Hello everyone, I'm Melek and today we're going to be exploring circular motion in IB physics. We'll look at both uniform circular motion where the speed stays constant and non-uniform circular motion where the speed changes. Throughout this video, we will break down where the key equations are coming from. We'll also look at different physical scenarios and we'll connect these concepts to IB style problems as well as some past IB questions so you can see how to apply them in real exams. So let's get started. First of all, I'm just going to go through some new concepts that we're new to, starting with centripetal force, which is the name given to any force which results in a motion along a circular path. We're going to be diving more deeply into this diagram in just a moment. And if we were to consider an object of mass m moving with a constant linear speed v in a circle of radius r, the linear speed could be calculated from 2 pi r over t. We know that 2 pi r is the perimeter of the circle, and t being in this case the period of the motion, which is basically the time it takes to complete one full rotation along the circle. So it's 360 degrees. We also commonly refer to angular velocity, which is shown by this symbol, omega, which is the rate at which an object rotates. So the rate here meaning that it's divided by time. And in the context of uniform circular motion, the vector nature of a constant angular velocity is not really important. So that's why it's also sometimes called angular speed. And it can be calculated through the formula 2 pi over t, as well as 2 pi f. F in this case being the frequency of the motion. And we know that we can calculate it through the formula 1 over t. And that's why we can combine these equations in order to find omega. Now here I've plotted a very simple diagram showing a uniform circular motion, and we're going to go over where the equations of circular motion come from. So first of all, as you can see, we have a velocity vector which is tangent to the circle. We also have a position vector. It's pointing away from the center of the circle. That's why it creates a 90-degree angle with the velocity vector, and they're perpendicular to each other. And since as you're going around in a circle, your velocity is constantly changing because your direction is changing, this is exactly what creates the centripetal acceleration. And we know that we can calculate acceleration through the formula delta v over delta t. And we can rearrange this to calculate centripetal acceleration, which is v squared over r. And the centripetal acceleration vector is always pointing at the center of the circle. And from Newton's second law, we know that F equals ma, and we can use this formula replacing a with v squared over r in order to get m times v squared over r equaling F centripetal, the centripetal force. And in the second diagram, we can see the omega, the angular speed, and we can implement angular speed into the calculation of velocity, which is in this case v equals omega times r. And we can use this previous equation here, replacing v with omega times r, and then the r's would cancel, so it's the centripetal acceleration would equal omega squared times r. And this is another way of finding centripetal acceleration. These are some of the most simple formulas that we're going to be using in circular motion questions, and that's why it's important to go over them before we start. And again, from Newton's second law, we could replace acceleration with omega squared times r in order to get m times omega squared times r equaling the centripetal force. Now these four formulas are going to be our basics when solving UCM questions. As you can see here again, F is equal to mv squared over r, which is also equal to m omega squared times r. Now we're going to solve a simple question to improve our understanding of what I was just talking about. So let's say a ball is tied to a string and rotated at a uniform speed in a vertical plane. The diagram shows the ball at its lowest position, and it's asking us which arrow shows the direction of the net force acting on the ball. So the net force is the centripetal force, F centripetal. And if I were to complete this to a circle, it's a rather wonky circle, but we could easily see that the vector pointing at the center of the circle is vector A, and that's going to be our correct choice, as we know that F centripetal always points at the center of the circle. And in this question, which is a real-life example of a car making a turn in a circular motion, it's asking us which force keeps the car on the track. So the answer to this would be the friction force, as the car is making a turn and it wants to keep moving this way, but the friction keeps it along the circular path, and that's exactly the reason why you can sometimes feel going outward a little bit when you're making it through a curve like this. That's why the friction force here is providing the centripetal acceleration, and the friction force is directed to the center of the circle here. And then we're asked to draw a free body diagram for this car. Now, beginning our free body diagram with the weight of the car as always, and IB likes to ask the drawing of free body diagrams, so this is quite important for uniform circular motion questions. First of all, as I said, we have the mg, the weight of the car, and this is balanced by a normal force as the object is going on a surface. And then we would show the friction force like this, pointing at the center of the circle. Now remember, this isn't the centripetal force as a separate vector because it's never shown on free body diagrams. This is quite important. The friction force provides the centripetal acceleration, and that's why it's shown as F friction. We're asked to derive the equation maximum V to make the turn safely. Okay, so we know that the F centripetal is provided by the friction force, so we can make them equal. And we knew that F centripetal is calculated by mv squared over r, and F friction is calculated by mu times normal. Now, since in this case normal balances the weight out, we could put mg instead of normal. They're equal to each other. And this would cancel the m's out. And as you can see, we're left with v squared equaling, if I put r to the other side, mu times g times r. So v would equal square root mu times g times r. And that is the derived equation. Now, another classic in circular motion are the roller coaster questions, where the object is going through, as you can see, a loop, and we're shown the highest and lowest points of the object. So let's begin by drawing the forces that are acting on this car at its lowest position first. So of course we're going to have the weight, mg, which is calculated by m times gravity, and then we're also going to have a normal force, which is pointing towards the center of the circle, as it's creating a 90-degree angle with the surface. This is the normal force. And in this case, the normal force is going to be larger than mg because it is going to provide the centripetal force. And that's why F centripetal can be calculated by normal minus weight. And in the right case scenario, we also have the weight, which is always acting downward. And since now the surface is here, the normal has to be perpendicular to the surface as always. So in this case, the normal and mg are going to be in the same direction actually, like so. And therefore, since we have two forces pointing at the center of the circle, we are going to add them up in order to calculate F centripetal. So in this case, F centripetal will equal normal plus mg. In this question, we have a bucket of water spinning in a circle, and in part A, we are asked, what is the minimum linear speed that's needed to keep the water in a bucket rotating in a circle of radius 0.95 meters? Okay, so in this position of the bucket, we just talked about mg and normal being in the same direction, which is going downward. So I'm just going to draw our forces right here, and normal. And in order to keep the water in the bucket rotating without losing contact with the bucket is by making the normal equal to 0. And if I take normal as 0, that would mean that the F centripetal in this case is provided by the weight only. So we knew the formula for F centripetal is mv squared over r, and the weight is just mg. And if I were to cancel these m's out, I would get v equals square root gr. And if we plug those numbers in from the question, we know that the radius is 0.95 meters, and the g is constant. It's 9.8 and 0.95. And that would just, doing it from the calculator, would give us v equaling 3.05 meter per second. So that's the answer for part A. In part B, we're asked what is the minimum angular velocity needed. So the angular velocity we know is referred to as the symbol omega, and the formula relating omega with velocity was omega equals v over r. And since I've already calculated v in the previous question, I could just plug those numbers in as 3.05 divided by 0.95, and this would give me 3.21, and the unit on omega is radian over seconds, as it's angular speed. That's where the radian comes from. And this is the answer for part B. In part C, we're asked how long will each rotation take if the buckets could be kept moving at the same speed. So this question refers to the period of the motion, and the formula relating period with omega is omega equaling 2 pi over t, which is the period. And then if I rearrange this in order to pull t out, I would get t equals 2 pi over omega. And just plugging in those numbers, I would get t equaling 2 pi over omega we found as 3.21. And doing this operation from my calculator would give me 1.96 seconds as the answer to the period. And then lastly, in part D, we're asked what maximum pulling force would be needed to maintain that speed if the bucket and water had a combined mass of 2.1 kilograms. So the maximum pulling force would occur at the bottom of the circle. Let's say I just complete this circle, and the bucket would be here. Therefore, the weight would point downward. Normal would point inwards towards the center of the circle. And since this position occurs at the bottom of the circle, we know that in this position, F centripetal is calculated by normal minus mg. And in this case, there's an arm that's doing the motion. Therefore, there's a tension instead of normal. So I could just replace those two. And the same goes for questions with a rope or a string attached to the object as well. So if I just pull tension out from here, I would get tension equals F centripetal plus mg, and then this would give me mv squared over r plus mg as tension. And plugging those numbers in again from the question, we know that the combined mass is 2.1 kg. V I already calculated as 3.05, so we'll just take the square of that. And r was 0.95 and plus mg. And doing this operation from my calculator would give me 41.2 newtons, since this is a force. And that is the solution to this bucket question. Here we have a car getting over a hill with a radius of 5 meters, and it's asking us what is the maximum speed that the car can travel safely without losing contact with the ground. So again, this is a popular question in IB style exams. In order to solve this question, again, we would draw the forces acting on this object. First we have the mg, and now since this car is going on top of the surface is here, the normal is going this way, perpendicular from the surface, so the normal is going that way. And since we're talking about the exact moment where the car is about to leave the contact with the ground, we can say that the weight is at this very instant greater than normal. Therefore, F centripetal here could be calculated by weight minus normal. And in order to make the speed maximum, I would again just make normal 0. So the F centripetal would be provided by weight in this case again. And F centripetal, as we know, is mv squared over r, and weight is mg. I'm canceling the m's out, and I would get v equaling square root gr. And if I were just to plug in those numbers, and the radius is 5 meters, this would give me 7 meters per second. And that's the answer to this question. And in this UCM question, which is a past IB question, a cyclist moves at a constant speed around a frictionless circular track of radius 5.2 m that is banked at an angle of 18 degrees to the horizontal. So it says that here, this angle theta is 18 degrees. The cyclist and his bike have a combined mass of 62 kg. What is the fastest speed the cyclist can travel at if he does not slip on the track? Give your answer to 2 significant figures without a unit. Okay, so this is an example of a banked curve. It makes an angle with the horizontal. And here what we would do is begin with drawing the forces. First of all, we have mg as always. And as you can see in this example, since the surface the man is going on is at a banked angle, the normal is going to be perpendicular to this surface. And that's why it's going to be at an angle as well. This is going to be our normal. It's not going to be in the opposite direction of mg. This is a common mistake. Don't do this mistake. And therefore, since this is at an angle, what we would do is we would separate this into its components, so we could see more easily. So this is going to be the normal's vertical component, and if I could just easily carry this angle theta to here, this would be angle theta, and then this vertical component would equal n cosine theta, and its horizontal component, which is going to go this way, would be n sine theta. And as you can see, the circular motion of this object would be sort of like that. And now we could easily see that n sine theta is what's providing the centripetal force in this particular question. So now in the vertical we have n cosine theta and mg, and they're going to balance each other out. So this motion is in vertical equilibrium. So that I could easily make them equals mg. And I also know that n sine theta is providing the centripetal force. So I could say n sine theta equals mv squared over r, which is the centripetal force. And now from here, I could just make things easier by dividing these two together. N sine theta over n cosine theta, mv squared over r over mg. And now from here, I could see that this turns into tangent theta, and the m's would cancel. This would give me v squared over gr. And then afterwards, we could say, if I cross multiply, v squared would equal tangent theta times gr, and v would equal square root of tangent theta gr. So if I were to plug the numbers in, I'm just going to do it here because we're out of space. The angle was 18 degrees. G is constant. and my radius was 5.2. And doing this operation from the calculator would give me 4.07, which is approximately 4.1 meter per second, as it's asking our answer in two significant figures. And that's the answer to this banked curve UCM question. So here we have another past IB question. A ball of mass 0.25 kg is attached to a string and is made to rotate with a constant speed v, so it's again a UCM question, along a horizontal circle of radius r, 0.33 meters. The string is attached to the ceiling and makes an angle of 30 degrees with the vertical, as it's shown here. So first of all, we're asked to draw and label arrows to represent the forces on the ball in the position shown. First of all, we have our mg. The ball has to have a weight acting down. And then since we have a string right here, this is going to provide a tension, which is acting away from the object. I could label this as tension. And this would be the answer to the question. There are no other forces that I would show on the free body diagram. Number 2 is asking us to state and explain whether the ball is in equilibrium. So the answer to this would be simply no. The ball is not in equilibrium. This is because the ball is in vertical equilibrium but not in horizontal equilibrium, because the horizontal component of tension provides the centripetal force. So if I were to, again, separate this tension into its components, this would be the vertical component. If I carry this angle 30 degrees to here, this would be 30 degrees. This side would be t cosine 30. And the horizontal component going this way would be t sine 30. So as you can see, the ball would be in vertical equilibrium as t cosine 30 would equal mg, but there is no other force on this side to balance the horizontal component of tension, which is t sine 30. So it's not in equilibrium. We could also see this as the vector pointing at the center of the circular motion is t sine 30, and that's why it's providing the centripetal force in this question, and it is what keeps the ball moving in a circular motion. And lastly, we're asked to determine the speed of rotation of the ball. So as we did in the previous question, again we would equal the horizontal and vertical components to each other. So as I said, t cosine 30 would equal mg. These are the vertical ones. And t sine 30 is what's providing the centripetal force, which is mv squared over r. Again, I could simply divide these two. And again, I would get v equals square root of gr tangent theta. From here, I could easily substitute my values into the equation. R is given as 0.33, and we have tangent 30. This would give me the answer of approximately 1.37 meter per second. And that's the answer to the speed of rotation of this ball. Lastly, we're concluding the video with a non-UCM question example, which is this turning table. There is an object of mass 20 grams, and it's spinning on a turning table with a radius of 50 centimeters, and it's asking us to find the maximum velocity of this object so it doesn't slide off. So first of all, in this question, we should be able to see that F friction is what's keeping this object on track. If there wasn't friction, this object would slide off. It would want to go outside of this track. and F friction, which is in this position acting towards the center of the circle. For example, if the object was here, it would act this way. It is providing the centripetal force. So we could easily write this as F friction equals F centripetal, which also equals mv squared over r. And F friction also equals mu times normal. So we could easily write the equation as this. And this would turn into mv squared over r equals mu times mg, because the normal is equal to the weight. And again, canceling the m's out would result in v equaling square root of mu times g times r. And this would give me 0.2, which is given as the coefficient of friction in this question, times 9.8 times the radius, which is, be careful, given as a centimeter, so I have to convert that into meters. This would simply make 0.5 meters. And if I do these calculations, I would find V as 1 meter per second. And this was the solution to our last question. Hopefully you found this video helpful, and we'll see you next time.